at the agenda, and the third talk today, it should really, for the authors, it should read Paul Matter, Elizabeth Biddinger, and Umit Ozgun from Ohio State. There's one other change. If you go 2 pages back and mark there on the posters, the third poster, it got copied over somehow from the second one, and the title should read Nitrogen-containing carbon nanostructures used for oxygen reduction catalysts in chem plus direct methanol fuel cells. It is correct in the abstract in the back, but if you make a note of that, I appreciate it. I'd like to go on and introduce our second speaker of today. David DeVillers is our speaker, and he is with the Photocatalysis Research Group, Department of Chemistry in Stellenbosch University in South Africa. So Bert gave him a very nice introduction for all the South Africans. And also with the Medical Research Council in Tygerberg, Cape Town, South Africa. His presentation will be on fundamentals and applications of TiO2 photocatalysis. Please help me welcome David.
Good morning, everyone. The work that I will be discussing today is on titanium dioxide photocatalysis, and this research was actually done several years ago during my graduate study at the Department of Chemistry in South Africa, and it was in collaboration also with the Medical Research Council of South Africa. Now, if we talk about titanium dioxide, the obvious first thought is it makes a good support for heterogeneous catalysis, to load some metals onto it and do some chemistry. But in this particular case, the titanium dioxide is actually the catalyst as a photocatalyst. So what we'll be discussing today will be around the activation of titanium dioxide by exposure to ultraviolet radiation. Now, just a quick overview of the talk. I will just want to highlight some ideas on titanium dioxide, the semiconductor photocatalysis, and where it fits into the broader range of technologies called advanced oxidation technologies. And what I'll really be focusing on is photocatalytic oxidative degradation. There are other type of reactions also done with titanium oxide. I'll also focus on reduction, but for the most part, I'll discuss the mechanism of oxidative degradation and how hydroxyl radicals and other oxidant species are generated. Then I'll just spend a few moments on the two main crystal structures of titanium dioxide, anatase and rutile, and try and give you an explanation as to why anatase is a better photocatalyst than rutile, and then just quickly give you a glance of some other semiconductors that are also considered. In our research laboratory over the span of about 7 years, and again, this is not very recent work, I'll just try and give you an idea of some of the practical laboratory scale reactor designs that we consider for investigation to be able to arrive at a commercial type of reactor, and then just give you an assortment of experimental results where we use photocatalytic oxidation of various dissolved organics in water media. Towards the end, I would just like to show you an example of photocatalytic reduction, which is not to do with oxidation, but rather with separation of platinum group metals, and also something that was not investigated in our lab, but is done a lot in Japan, is the effect of superhydrophilicity by way of titanium dioxide photocatalysis. And then finally, just some strategies on how to improve the catalyst. Well, first off, with advanced oxidation technologies, it's really a whole family of oxidation technologies, and the only real one in this whole group that is to do with heterogeneous catalysis is semiconductor photocatalysis. But for the most part, these technologies involve the generation of hydroxyl radicals, hydrated electrons, and hydrogen atoms, and they all go through the same steps, namely the generation of carbon-centered radicals, peroxyl and oxyl radicals, and then finally decomposition to alcohols, ketones, and CO2 and water. So I'm not really going to focus on these particular areas, but chemical oxidation technologies, for example, involve the reaction of ozone with hydrogen peroxide to generate the oxidant species. Just to give you an idea of the semiconductor photocatalysis, it is really a conventional heterogeneous process which has to do with the main events that one typically encounters with heterogeneous catalysis, namely the transfer of the liquid or gaseous phase reactants to the catalytic surface, adsorption of at least one of the reactants, reaction in the adsorbed phase, desorption of products, and removal from the interface region. So it's a typical heterogeneous catalysis setup. But the main difference here is, as opposed to how we look at metals on supports, where we would take a reducing agent, or maybe together with temperature to reduce to a metallic state, we are really looking here at photonic activation. Just to give you a little bit of revision, if we look at metals versus semiconductors and insulators, really with metals, at 0 Kelvin, all the electrons are in the valence band, and for any temperature above 0 Kelvin, there's a free flow of electrons to the conduction band. With insulators, on the other hand, the band gap is too large to use something like ultraviolet or visible light. When we look at semiconductors, the valence band is typically around 2 to 3.5 electron volts, which allow for potential activation and charge carrier separation to allow for reduction and oxidation reactions. I just want to focus on this particular slide on titanium dioxide's mechanism for photocatalytic oxidation. To set the whole process in motion, one starts with the titanium dioxide colloid particle, and if one uses the band gap model, the reaction is started by irradiating with ultraviolet light. Now with titanium oxide anatase, this band gap corresponds to an energy of about 3.2 electron volt, which again corresponds to a wavelength of about 388 nanometers. So we are just in the UV range, where 400 nanometers is roughly the demarcation between visible and ultraviolet light. So when the particle is irradiated, there's a charge carrier separation. A photogenerated hole is left in the valence band, and an electron is activated or excited to the conduction band. Now at this stage, one needs this charge carrier separation to remain going for a while to enable the participation of these species in redox reactions. One would typically, with a water environment around the particle, if one assumes this is a titanium oxide colloid suspension, have a monolayer of water or OH minus ions, depending on the pH of the system, then be oxidized by the photogenerated hole to create hydroxyl radicals. At the same time, what will happen is that the hydroxyl radical, through abstraction of protons from organic pollutants that may also be in the vicinity of the photocatalytic surface, go to organic radicals and water. Then at the same time, while this is taking place, the electron in the conductance band will participate in a reaction to form oxygen radical anions that are really considered as so-called supercharger of the photocatalytic process, which will also then participate in these organic radical reactions to further decompose the organic media to CO2 and water. So But what we need to understand here is the oxidation potential of the photogenerated hole is larger than the reduction potential of the electron in the conductance band. And really the photocatalytic efficiency, which has always been the problem with this technology, taking it forward to the next level, is that the rate of recombination of the conductance band electron and the photogenerated hole is always too fast in correspondence to the rate where it's generated. So the other important point is that the surface catalyzed oxidation is happening in the proximity of the interface and not in bulk solution. Now, in a situation where one is working with very concentrated organic media, the organic media is likely to react with the photogenerated hole rather than forming the hydroxyl radical. And with any catalytic process where you're cutting out some steps, you're making the photocatalyst process more efficient. And in this particular case, one will also then lead to degradation here. One final step that I'd like to mention is that there are some strategies to increase the lifetime of excitation by depositing noble metals, platinum group metals. One typical example is palladium, that will facilitate interfacial electron transfer to the oxygen in the surrounding medium to form the oxygen radical anion. And by doing this, one can counter a rate limiting effect from forming this species. Just to give you an idea of associated times with these processes that I've discussed, the charge carrier generation is typically in the order of femtoseconds. It's very fast. Then the reaction of the photogenerated hole is about 100 nanoseconds. The electron is a shadow trap, is 100 picoseconds. And then there's also a so-called deep trap if it's deeper and not into the surface. Both the photogenerated hole and the valence conductance band electron must migrate to the surface of the particle to enable its participation in reactions. Again, a higher quantum efficiency is achieved by faster interfacial electron transfer rates or slower charge carrier recombination. There are some strategies I'll point on that later on. Just to give you an idea from the perspective of water treatment, the oxidation potential of hydroxyl radicals versus other oxidants, it's just about fluorine is higher in oxidation potential than hydroxyl radicals, so it's pretty high up, so there's a good oxidizing ability there. You see standard things like chlorine is way down here. Now, the hydroxyl radicals, because of their short lifetime, is very difficult to detect. Some people have argued that they've detected these radicals in ice, trapped them in ice, and then detect by electron spin resonance. But for the most part, it's an indirect detection by using spin trap and probe molecules. These are a list of these molecules, but the one that's really used the most is this dimethyl ferrolidone in oxide. And what is indirectly detected is the hydroxylated DMPO product through electron spin resonance spectroscopy. And in some cases, like with silicic acid, we also use HPLC. Just to give you an idea of the kinetics, typically, as one can expect, the kinetics are often derived for these photocatalytic oxidation reactions by disappearance of the reductant, which might be the organic molecule, or the consumption of oxygen. And it will have this kind of dependency that assumes that with the rate determining step of the process, we'll have a monolayer of both reductant and oxidant at that interface. Then a lot of rate determinations in the research. One sees the Langmuir-Hinshelwood equation, which gives you the proportionality factor related to the reactivity of the titanium dioxide, which in this case might depend on the amount of light absorbed by the titanium oxide particle, as well as in flow reactor systems they have found the mass transfer dependence. Here is your Langmuir absorption constant. In general, this type of chemistry is used for very dilute concentrations of organic radicals, organic molecules. So you can also imagine that when it's very concentrated, you might have a color to your solution, so that might inhibit the penetration of ultraviolet rays. But in general, for 10 to the minus 3 molar or 1 millimolar, the reaction rate will often be first order, and as you convert your substrate to lower concentrations and oxidize these molecules to CO2 and water, the reaction rate can often be zero order in very high concentrations. So if the concentration is lower, it might be first order, but they've also talked about mixed order reactions where it might become second order. Anatase versus rutile titanium dioxide. If one looks at the redox potential on this axis, rutile and anatase, they have similar redox potentials over here in the valence band, but with the conduction band there's a slight difference. One would require light in the visible region for rutile, but what we can notice here is that this conduction band potential is very close to the potential for the photolysis of water in acidic media, so that reaction will rather be favored if one uses rutile as opposed to the formation of the oxygen radical anion as indicated here for anatase. So generally the photoefficiency of the anatase is better than with rutile. They also say that some crystal defects in rutile might be responsible for more positive hole and conduction band electron recombination. Crystal structures of these, of course, as we know, is that both are tetragonal formation. On various other, let me just go back to that slide one more time. If one looks at the oxidation potential for this reaction compared to that reaction, the difference is about 1.23 electron volts, and so one would be able to have the full decomposition of water and the formation of oxygen and nitrogen out of water, photolysis, which corresponds to 1.23 electron volts. So any semiconductor theoretically that overlaps with that kind of energy would be able to do that, although it doesn't exist. And if one looks at all these semiconductors that can be considered for photocatalytic activity, really the cadmium selenide is the one that comes closest to those two reactions of the full decomposition of water. But for the most part, these other semiconductors are not photostable. They tend to decompose upon exposure to ultraviolet light. So for the most part, in research, in many research labs, the focus has been on titanium oxide because of its photostability. Now we move on to some reactor designs. It's almost just like Fischer-Tropsch here. There's a slurry phased approach with titanium oxide suspensions, separation problems, just like you get with Fischer-Tropsch. And also then the second group is immobilized bed, where you can attach the catalyst to various mediums or materials. We have investigated in our lab the use of fiberglass, activated carbon, as I'll show you in a second. For the most part, people who are interested in mechanistic and kinetic studies will just build a simple batch reactor on a bench scale. But the people who look at scaling up will consider falling film or annular space reactors. Here's a typical example of an annular space reactor. This will be an ultraviolet lamp source, typically a low pressure mercury arc that emits radiation at 254 nanometer, which is sufficient for the activation of titanium oxide. And with your water containing your organic gluten going in here and going out there, so it's getting exposure in this annular area. Now, in most of our research and most research groups around the world use titanium oxide P25, which is roughly about 75% anatase, 25% rutile, just to give you an idea of some of the properties. as obtained from the GUSA website. I understand they've changed the name recently, or they're part of the Evonik Industries group now. Specific surface area around 50. Primary particle size is about 21, and when we did this research, they used to report it as 30. So in the process that they used to make the titanium oxide is going from titanium tetrachloride through hydrolysis to form titanium tetrahydroxide, and then through controlled drying they form the titanium dioxide. But the formation of the titanium dioxide is very heavily dependent on aggregate size. When your primary particles are smaller, they tend to aggregate faster or easier, so it's hard to control. There's just some of the other. One that I wanted to point out here is the compacted bulk density. It's fairly low, 0.13 grams per liter. Just some examples of lab scale falling film reactors. We were particularly interested in falling film reactors because we wanted to prevent the situation where UV light might be stopped by excessive penetration of thick films. So we focused on flow systems where falling film would be created by pumping in the solution into a cup in a tubular reactor arrangement with some ultraviolet lamps surrounding it. And when the cup is filled, it would overflow as a cascade down to the bottom and then be recycled. So that was one of the systems we looked at. Just some typical results we obtained. This was for a slurry type of reactor. You can see for a model organic pollutant, which was easy to follow by UV-vis spectroscopy. Parachlorophenol is a typical industrial water contaminant. An increase in removal rate over time as one would increase the concentration to about 2%, but then at 30% the level would start increasing again, which had to do with excessive absorbance. We also looked at slurry effects, and one can see the efficiency of the process dropping off at higher pHs, which had to do with the interaction of phenolate ions and the titanium oxide minor species, which are very high in concentration at those pHs. So obviously one also needs good interaction at the liquid particle interface. Just some more examples. A very clear result here showing that the presence of oxygen is needed to generate the superoxide radical anion, which facilitates the oxidative degradation, as opposed to air and argon. The argon experiment would just amount to a process that generates hydroxyl radicals. And this particular case is just response surfaces we generated, showing on this scale the suspension loading going through a maximum, and on this scale the flow rate, showing the dependence on film thickness, which was anything from about 50 to 300 microns. An example of many experimental designs that we did in this particular study for this reactor, looking at catalyst suspension loading, flow rates, gas purge, the rate of gas purge, initial concentration levels, and also the distance of the irradiation source from the surface of the film. And what we have found is that the gas purge plays a big role, as we've shown you before, as well as the suspension loading. The second reactor was of the immobilized type. We obtained a commercial fiberglass that was reinforced with a mesh and designed a falling film reactor, slightly different than the other one. Obviously, you can imagine the advantage of such a reactor is to have modules of these in series to effect the degradation. And we also did the coating of this fiberglass sheet module with different techniques, spray coating, suspension loading, so forth. There you can see some of the results. The catalyst suspension loading used for the coating, and then the obtained impregnation loadings. In other words, how much was loaded onto the sheet. And what you can see here is that beyond about 5 to 10 grams per square meter of the titanium oxide loading, it's more or less a stabilized effect in terms of oxidation. Yet another experimental design that was done, many variables at the same time, following the rate constants. And what we found here is that the UV source that we used had the highest effect, and what we did was we varied the ultraviolet lamps we used from the UVA genocidal lamps at 255 nanometers to the fluorescent black light, which was a whole range of wavelengths, seemed to work less effective. We also ventured into activated carbon for a while. We weren't very successful, but what we have here is woven carbon fibers. We call it fibrous activated carbon. There's the arrangement in the falling film reactor. What we try to do is have areas of just carbon adsorption followed by areas of titanium oxide photocatalysis. Unfortunately, what we found in this study was that the rate of adsorption far superseded the rate of photocatalytic oxidation, so we left it at it was just, absorption was just too strong. Just to give you some ideas of this material, we work with grade 15 and 20. It's a very high surface area woven carbon. Here you can see the SEM profiles, 10 microns diameter for these individual fibers. Our attempt at coating it wasn't that successful. These activated carbon fibers were obtained from Japan, and they were typically made from natural precursors such as coconut or synthetic precursors like resins, carbonization at 100C, and then steam and CO2 activation to get that high surface area. But as I mentioned, the effect of carbon adsorption was way too strong to be able to detect any benefit of titanium oxide catalysis. Then our research with the Medical Research Council was around biotoxins that were observed in some domestic water supplies in South Africa. This is also something seen to some extent in China, in Brazil, and also in the United Kingdom, is that from time to time, especially in the summer months, certain estuaries and lakes would have blue-green algae because of excessive eutrophication and pumping in of, for example, sewage and things like that. And these algae will then liberate toxins that are extremely potent into the water. So the part of our research was to see if we could degrade this very stable structure, and even through domestic water treatment, for example, boiling of water or sand filters, these structures remain intact. Just to give you an idea of the toxicity of these molecules, it's roughly 10 times the toxicity of sodium cyanide if one looks at the LD50 value for intraperitoneal injection into mice. The toxins are amino acids, 7 of them. 5 of them are fixed amino acids, but 2 of them are variable amino acids in the X and in the Y position, and they have roughly up to now identified about 60 of these analogs. You can see it's fairly high molecular weight organic molecules. For the most part, we have focused on LR, where X equals tyrosine and Y, sorry, X equals leucine and Y equals arginine in these variable amino acid positions. So it's just an indication by HPLC showing you the different analogs of this toxin in the water that we analyzed. Send them through the photocatalytic reactor and get the full mineralization, just the formation of CO2 in water after about 20 minutes of exposure. So just one result that we tried with the fibrous activated carbon and titanium oxide. Here you can see without the titanium oxide or without the ultraviolet light, which is basically sort of a mass transfer effect and no degradation. But with the ultraviolet light activating the catalyst, there's a photocatalytic oxidation. All right. Just very quickly, a photocatalytic reduction is another application. Just the same mechanism as we've discussed before, but if one uses a sacrificial reducing agent like ethanol or sugar to trap the photogenerated hole, one might be able to use that electron to reduce some metal species in solution. So this technique might be used to separate platinum group metals in solution, but it can also be used to prepare catalysts. This is the procedure that we developed in the lab, was to have a mixture of platinum, palladium, and rhodium at high pH. You have selective absorption. The platinum remains in solution, but the palladium and rhodium goes into the titanium oxide, and then at lower pH there's selective reduction of the palladium. Just to show you the reactor configuration. It's a very simple batch reactor with a photoreactor there. And there you can see, as a function of time, the rhodium staying relatively constant and then settling out the reduction of the palladium due to the help of the sacrificial reducing agent. Same thing here. We used ethanol, different concentrations of ethanol, different rates of removal of rhodium. In this case, it was just a rhodium solution. There were no other metals. This one I'm not going to talk about now. I think we're a little bit pushed for time, but what we essentially have is during photocatalysis you can have oxygen vacancies on the surface, which can then be occupied by water that's coming from a molecule such as silica that can produce water or make water available to complex on the titanium oxide surface. And in doing so, one can change the hydrophobic character to a hydrophilic character. Just some examples from Japan where this hydrophilicity has been applied. Of course, one will have to make the photocatalyst more responsive to visible light to make this a practical situation. It's sort of anti-fogging due to hydrophilicity increase in this area. You can see the contact angle in this case might be much higher between water and the surface compared to here where the surface has been treated with titanium oxide. Self-cleaning due to the hydroxyl radicals oxidation potential. Some applications in operating theaters, self-cleaning as well as in cars. These are Japanese examples, not ours. And then just the final slide is strategies on how to improve the photocatalyst. Unfortunately, there's only about 5% photo efficiency, and this has been over about 15 years and still continues to be the problem today in scaling up the technologies to utilize the ultraviolet light and to generate enough oxidant species. And there are several methods to try and approach this. It mainly involves surface perturbation or modifying the electronic structure, different chemical approaches. And this is the one that we looked at, is the co-deposition of platinum group metals. So thank you very much for your attention.